Hi, in this video we're going to look at graphs of rational functions, and actually we're just going to begin talking about the initial stages of graphing a rational function. First of all, let's define what a rational function is. As you can see, I have f of x is equal to p of x divided by q of x. In other words, it is a ratio. And an example of a rational function would look like this. If we were trying to graph this, we'd first have to understand some characteristics about it. And first of all, there are horizontal asymptotes oftentimes associated with rational functions, and there are vertical asymptotes and sometimes point discontinuity, which basically means there's a hole in the graph. So there's just a lot of different things that could be going on in a rational function. So for all practical purposes, we're going to take a look at this left side of the flowchart first, and in another video we'll come back and look at horizontal asymptotes. But to find what's going on as far as vertical asymptotes or point discontinuity, and sometimes you have neither, and that's not even showing up here on this flowchart, but you'll soon find that out as you just go through the process of this flowchart. At any rate, you start by factoring out the numerator and denominator, which is a common theme in rational functions or expressions in themselves. Once you have factored it, you're going to ask yourself this question: are there equal factors in both the numerator and denominator? Based on that answer, that will tell you what direction to go. So let's just say the answer is yes. Well, that would mean that there is a point discontinuity at that location. And from there, what you would do is you would simply cancel out the factors and you would graph the function, but you'd have to place a hole where you made this cancellation. If the answer is no, then more than likely you have a vertical asymptote, and that vertical asymptote is located at every undefined value in the denominator of the function. So if we were looking at this example right here, we'd ask ourselves the question, are there equal factors? And the answer to that is no. Keep in mind, equal factors don't mean equal terms. These are equal terms. They're not equal factors. So keep in mind, you can only cancel out groupings that are the same. And that's just simply not the case here. So the answer to this would be no. So more than likely we have a vertical asymptote. And that vertical asymptote occurs at the undefined value. So we have a vertical asymptote at x equals 1. In other words, a vertical asymptote is a vertical pole, so to speak, that the graph approaches but does not cross over. So let's take a look at a few examples from homework. This is from page 495, and you start again with the question being asked here is just describe the vertical asymptotes and holes for the graph of each rational function. So we want to go again through that flow chart, make sure that the numerator and denominators are all factored. In this case it is. Then asking ourselves, do we have equal factors in the numerator and the denominator? The answer to that is no. And so we have vertical asymptotes, and notice you can have more than one. Each vertical asymptote is going to occur at the undefined value here. And so the undefined values occur when x creates, where x makes the number equal 0. So in this case, x is equal to -3/2, and that is obtained simply by setting that equal to 0 and solving it. And x is equal to 1. And I want you to notice that I used the abbreviation VA for vertical asymptote. So this shows me that I have two vertical asymptotes. One is at x equals -3/2, and one is equal to x equals 1. Now notice again, it's not asking me for the domain. If it was asking me for the domain, I would strike a line through this equal sign stating that we can't use these values. In this case, a vertical asymptote is what is standing in the way there. It's that pole that is there. So the graph actually approaches that vertical asymptote, and that's where it occurs, right at that undefined value. Okay, let's take a look at number 14. Okay, we need to first of all factor the numerator and the denominator, x plus 2x minus 2, because that's the difference of two perfect squares. And now we ask ourselves, do we have equal factors in the numerator and denominator? And the answer this time is yes. These two are equal. So we do not have a vertical asymptote, we have a hole. And that hole occurs at the undefined value, which is x equals -2. Keep in mind, you do need to put the x equals -2, not just -2. That's oftentimes a mistake that's made. Okay, number 17. Again, we're going to factor both numerator and denominator. And I see in that denominator I can factor out a 2. Keep in mind, once again, you can't strike these 2x squares because you have this plus 2 here. This plus 2 is connected to this 2x squared. And it doesn't mean you can strike out at equal terms. You have to strike out equal factors. So in this case, we can strike out the 2's because they're factors. Next, we look at this and we say, okay, we now have x squared over x squared plus 1. Can't strike out those x squares because they're not common factors. So what we're going to do is we're going to look to see where x squared plus 1 is equal to 0. Well, I put this one on here purposely to show you that sometimes you don't have a vertical asymptote at all. In this case, we wind up with an imaginary solution, and so in this case there are no vertical asymptotes whatsoever. There's no holes and there's no vertical asymptotes. So that's how you do these questions, so good luck on the rest of them.